Good morning, everyone. It is a privilege to stand before you today, the 2025 Lubricant Expo North America. On behalf of Citgo and the show sponsors, we are extremely grateful for you to be here today as part of this growing event. It's fantastic to see so many industry leaders, innovators, and experts here to discuss the future of our industry. While lubricants doesn't always make the headlines, our industry plays a crucial role in keeping the world moving, supporting everything from transportation to manufacturing, energy production, and beyond. We are the business behind business, ensuring reliability, efficiency, and sustainability in nearly every sector. As we look ahead, we recognize the challenges and opportunities that will shape our industry: evolving fuel technologies, electrification, sustainability demands, and the rise of AI-driven innovation. These shifts demand both technical expertise and strategic collaboration, which is exactly what this show is about. Over the next 3 days, I encourage you to take full advantage of the knowledge being shared, engage in meaningful conversation, and forge the partnerships that will drive our industry forward. Let's make this an event that not only informs, but also inspires action. Thank you, and let's have a great conference.
Good morning, everybody. Thank you for coming. This first plenary session, leadership panel apparently on future fuels and their impact on lubricant requirements. There's a couple of things we need to go through from a housekeeping perspective. In case of emergency, please follow the instructions provided over the public address system and exit via the nearest exit sign. Kindly ensure your mobile phones are off. We don't want to be disturbed while we're having these essential discussions this morning. Flash photography and taking photographs of slides are not permitted. Please do not do so. I will call you out if I see you doing it. And they will be available, permissible slides will be available online after the conference, and you'll be given a means of getting access to those. The Q&A will take place during the discussion period towards the end of this session, and you can submit your questions via the Slido app. So if those of you who do not have the Slido app, please proceed in downloading that so that you can ask those questions. So I will be moderating this session. We have 2 speakers. I apologize, we have lost some due to various reasons, travel restrictions and concerns over shifting political requirements and ideas. And we will be proceeding with our 2 speakers, if you'd like to come up. And then we will be having Raf Britton join us for the question and answer session towards the end of this session. For those that do not know me, I recognize most people in the audience, but those that don't know me, I'm Peter Lee from Southwest Research Institute, where I'm an institute engineer and the chief tribologist. Our first presentation is by Troy Moransky, who's the lead organic materials engineer from American Axle and Manufacturing. Troy received his BS in Chemical Engineering from the University of Michigan and his BS in Chemical Engineering from Wayne State University. He has over 17 years in the automotive industry and has held various roles in materials engineering, process engineering, environmental engineering, analytical chemistry, quality, and laboratory management. Troy's technical expertise is focused on lubricants, surface treatments, and coatings, with most of his career being centered around research, development, testing, troubleshooting, and product launches of organic materials used in driveline applications. He currently serves as the chairman and ASTM D7452, that's the L42, reviewer for the Lubricant Review Institute, and for all SAE J2360 gear oil approvals, and he's an active member of ASTM, SAE, API, and the STLE.
All right, good morning, everyone. So today, as Peter introduced myself, we're going to be talking about future fuels and their impact on lubricants. So just kind of a general overview of kind of where the industry kind of is on the EV front. American Axle providing hardware for the industry for EVs, so that's where my talk is going to be focused around. So since 1990, right, you can see this nice trend on the screen here talking about CO2 emissions coming out of various sources, and they've continued to increase greatly over the years. So 2022 global emissions totaled over 37 billion metric tons. In 2023, went up to 37.5 billion tons, so quite a big jump. So this was a large increase, 400 metric tons year over year. I haven't seen the data for 24, but the expectation is going to be this continues to grow, even though, as a world globally, we're trying to reduce this number. And when you look at the distribution breakdown of where the CO2 emissions are coming from, right, the transportation industry and the power generation industry are your two largest chunks. So looking at the global footprint, right, the transportation industry is over 21% of that. Power industry is 38%, almost 40%, so a very large chunk. So kind of looking at the emissions, right, you would look at the power side of things and think, well, it's a big chunk. We should be focusing on that. And then with all the vehicles on the road, different transportation industries, 20%, that's where most focus is happening now. And there's been a lot of discussion kind of in the industry as far as is EVs really the future? Where are we going? And it's kind of shown here, 24 sales, right? There's a big trend up. So from what I've heard in the industry is there's been a lot of consumers that have been kind of pushing back, some OEMs pushing back, but yet the sales here are still showing that we're proceeding forward. We're still increasing. So, globally, 17.1 million vehicles sold year over year from 23, 24 is a 25% increase. So that's a big increase. A lot of different EV companies in the market now providing hardware. And the consumers still are obviously wanting to continue to buy these. So when you look at some of the reasons that this might be happening, and there's a lot listed here, I'm not going to go through every single one of them, but kind of each country's position themselves, I think, to try to help drive EV sales, to help clean up the carbon footprint. So looking at China, for example, when you buy a vehicle, you have to buy a license plate just like you would in most other countries. There, it can be more than $13,000 just for the license plate. But when you're looking at an ICE vehicle, you're going to have to pay that, where an EV, they've added an incentive, that fee goes away. And the average EV vehicle cost in China is only around $12,000. So if I have to pay twice that to use an ICE vehicle, it's definitely going to drive down using an EV. So huge incentive, and that's why China, I believe, is probably leading the market. Right now, I think they're around a 40% increase over the other countries. Norway, for example, just like other countries here, they're trying to give different tax incentives and different rebates, whether it's when you first buy the vehicle, maybe on your registration, different incentives back. France doing, 7,000 euros up to for buying EVs. So legislation is working. You have the governments that's doing incentives. The United States, for example, is another country that has had some, say 4 or 5 years ago, we had more. They kind of went away through COVID, and now we're starting to see them come back to try to drive sales up. But interesting enough, everything's showing that we're trending upward and we're selling, but yet a recent survey that was done, and the results came out last February, kind of shows a different consumer direction, right? So why are they not buying EVs? So if you consider the range anxiety, the charging timing, things that people have a lot of concern, right? For the weekend, I want to go away and drive 4 or 5 hours, maybe longer, and I have to start planning all my stops where I can find a charging station, hoping that I can find one that's actually open. I don't have to wait for somebody to charge. Normal gas stop, 5-10 minutes at most, grab snacks, use the restroom, and head out. So it's definitely a concern on the charging and the range anxiety. There's definitely some familiarity with EVs. If anybody's been in a newer vehicle, lots of buttons now are gone, right? Older vehicles used to have buttons everywhere. Now there's a touch screen that controls most of your vehicle. So a little bit of that unfamiliarity, But even more striking to me was this part of the survey, which showed people that currently own an EV, there's a lot of reasons why they wouldn't buy another one. And when you look at kind of the UK here in the US, half the current EV owners, at least based on this survey, would not buy another EV. And that's kind of counterintuitive when you look at the sales just increased year over year by 25%, right? It's a big jump on one side, but yet consumers are saying that we're concerned and we don't want to go this way. And even Norway, who's kind of leading that charge as far as the percentage of new vehicle sales, which I believe is around 98% today, 18% of their people wanted to go back to an ICE. So what's really the right direction? Are we going towards EVs? Are we not? As long as the sales continue, I would say we are. So, kind of the overview of the current state, government incentives, right? They're driving those consumers to purchase them, which the EV sales does include hybrids. So whether it's a plug-in hybrid or a true battery electric, all those incentives are taking place for those type of vehicles. So many of the OEMs too also kind of reevaluated in the last couple of years as far as what they were doing, whether they pulled back future programs, volumes, trying to adjust where the market was. I know this time last year there was a big kind of shift, some changes to some of the US legislation and other legislations trying to figure out where we're going and how we're going to get there. So when we kind of think about the future of the internal combustion engine as we know it today, gasoline fired, diesel fired, to me, it's going to be prevalent for many years to come. There's a lot of industries today that it really doesn't even necessarily make sense for. Yes, there are designs that are out there, but when you think more isolated areas, most of middle America today is farmland. Not all kinds of available charging stations, a lot of people using trucks and heavy equipment to move things. Maybe it's remote mining operations, whatever it might be. EVs aren't going to make sense for everything, even if we can get the consumer buy-in on them. And it's been around for a long, long time. So maybe we shift to a different type of fuel. Maybe we shift to a different type of combustion engine design. But all in all, at least for my stance, I believe that we're going to be going for an ICE for many, many years to come. Maybe that's 15 or 20 years or maybe even longer. And really, where the EVs seem to be selling the best, and I don't have a slide breakdown for this, but the hybrids seem to be the most popular option because you take away a lot of those range anxiety and charging concerns. And just overall, right, the impact on the lubricants when we talk about an EV. So you have all the consumer concerns, but when it comes to the lubricants and why we're all here today, there's a lot of current and new concerns. So first and foremost, I no longer have, at least for a pure hybrid, I don't have an engine and exhaust system making a lot of noise. And these are also going to be spinning at a lot faster speed. So because of that, the systems design have to be really, really well balanced, very high polished gearing surfaces to make sure there's no noise, vibration, or harshness. Nothing that the driver is going to experience that may be drowned out with a current exhaust system. You also have with these, because of the gear ratios, you're going to have a much higher cycle count on the gearings and bearings, sometimes 10 times or more, right? So all of those components have to be designed for a lot harsher durability and longer cycle count. You also have to be concerned about systems that have a 3-in-1 type unit, so the motor, the inverter, and the gearbox are all wet systems. And there is an E&M field that's coming off of that motor and possibly the inverter that's going to then kind of interact a little bit with the polar molecules, right? Magnetic field's going to shift those. And there's not a lot of studies yet, but I've seen a lot of concern in the industry about how that's going to impact the gearboxes as we continue to drive for higher output motors, higher voltage, higher amperage. And one of the things, and I know if you've been to any of my talks or industry events, aeration is always one of my biggest concerns. Most of your aeration in your gearboxes today, transmissions, engines, might see 5 to 10%. There's been, speakers at different companies that have came out and said that their oil has been seen to almost be a fog or a mist. And to have aeration up to 40 or 50% in a system isn't going to be unheard of. Depending on how the system's designed, how deep the sump is, the settle out time for the air, this is going to compound over time. So it's something that the lubricant manufacturers and formulations are going to have to address to try to minimize the entrained air as well as the air that comes out in foaming. Back tied to durability and heat transfer, these fluids are continuing to get thinner and thinner. Gear oils, for the most part, have kind of sat in the 9 to 12 centistoke range for most light-duty vehicles for, the last 10 years or so, though we are starting to see some of these come down into the 6 centistoke range. But when we talk EVs or electric vehicle fluids, I've seen fluids down all the way to 1.5 centistoke at 100 C. So very, very thin, going to be optimized more for the heat transfer of a wet motor type system. But it also creates a harsh system for the durability concern, right? Much thinner film, under heavy loads and speeds and cycle counts, all that are going to drive some really, really harsh requirements for the lubricant. And then when you talk, well, how do we test what we're trying to do? How do we ensure that we're creating a formulation that's going to work in whatever application design? The industry test methods, which there's a lot under development, lots of groups working on trying to develop them, it's a big gap today. So when you talk EV hardware, all the OEMs are typically in like a prototype phase. Getting hardware is really difficult, let alone getting time into test. It makes it really challenging for the lubricant manufacturers to try to say, yep, this is going to meet the requirement until I get it into your system. And finally, kind of the fill for life side of things. So a lot of the OEMs are saying, well, I want this in my gearbox for life. I don't ever want to have the consumer have to take it to the dealership to change the oil in it. And a lot of these systems aren't even designed in a sense where I can do a quick oil change. It's going to involve maybe dropping a unit out of a vehicle, dropping it down. Maybe there's not an accessible drain plug or even a refill location. So from a design standpoint, it's challenging. From a lubricant standpoint, well, what does fill for life mean? Is it 100,000 miles? Is it 200,000 miles? Is it in a very wet environment? So these are open to the atmosphere, right? Lots of different concerns that the lubricant manufacturers aren't going to really know how to address. So kind of wrapping up, what does this all mean? What does the future hold? EVs have already driven development of new additives and base stocks, new chemistries. I don't think I've went to a conference or an event over the last couple of years that everybody's not trying to find some sulfur replacement that can help protect the gear and bearings, but also is going to work well with copper. Is anybody that knows sulfur? It doesn't play well with copper. It's a big problem when you have these wet motor systems that there's a lot of exposed copper. Also trying to maximize efficiency of all of these, right? Everybody's talking about that mileage, that how far can I get? So I need to have these systems be as efficient as possible while also durable as possible. We don't want to have these systems breaking down on the side of the road. So minimizing your aeration, all these different influences are really pushing us into a new regime. And I think, at least from my perspective, the hardware is designed, and we're going to continue to push the limits on what we can do. And the lubricant companies are supporting and right there with us to try to help us figure this journey out as we go forward. So when we think about future fuels and what the lubricants are going to do, I think in the next couple of years, we're really going to start seeing a continued major shift towards some new chemistries, which I think are going to carry all the way back to all the different turn applications, whether it's transmissions or industrial gearboxes. With that, thank you very much.
Thank you, Troy. Just to remind you, in the Slido app, you can send those questions in at any time. I do not yet. Oh, I have one question. Thank you, whoever sent that question. Please keep those questions coming. So our next presenter is Jean-Dominique Bonnet, Director, Advisory, Frost & Sullivan. Jean-Dominique, JD, Bonnet has been a Director, Advisory for Chemical Vehicles for the growth advisory services firm Frost & Sullivan since 2018. He has had a varied career that took him from engineering to finance and then to strategy. He has developed a strong understanding and conviction that decarbonisation, including that of the energy converters involved in mobility, is best addressed through the broader lens of energy transition. This approach considers the specific conditions of each application while also accounting for scalability and economic value. By integrating these factors, he focuses on creating practical solutions that take the full life cycle into account and move closer to optimal outcomes.
All right, good morning.
I can feel the heat here. Everybody is so excited to listen to my speech. So I will not start with a joke because my wife is here and she says that I'm always telling very bad jokes. So I will go straight to a presentation. All right. So today, Troy has been talking about alternatives like going with a battery electric vehicle. The question is how we can eat an elephant. So the answer is we do it one chunk at a time. And what we are looking at right now is other alternatives like alternative fuels, and more specifically, I will be talking about hydrogen. So we'll go first through the ecosystem of hydrogen. I think it's a little bit interesting to understand why we are going with hydrogen and what are the benefits. And then we'll go into the specifics of how it applies to the engines and what are the requirements that puts on the lubricants. So if you look at the production of hydrogen worldwide right now, on the left chart, you have a global production, which is about 100 million metric tons of hydrogen. That's the unit that we are using. And you see the color, it's gray. It means that this is hydrogen that is produced using methane, and the methane that go through a steam methane reforming process, which means that basically we strip the carbon out of the methane, we combine it with oxygen, and we get CO2. And on the other side, we get the hydrogen. So that's not a process that is meant to be clean by today's standards. If you want to produce about 1 kilogram of hydrogen, you will produce anywhere between 8 and 12 kilograms of CO2. So that's the end user looks clean, so to speak, but there is something in between before that. If we now look at the chart on the right, it's specifically the US. So in the US, we use about 10% of the global production and demand of hydrogen. So we are at 10 million metric tons. And back 2 years ago, the Department of Energy, DOE, put a goal for us to increase the production by another 10 million metric tons between now and 2030. But the condition is that we want that increase to be clean hydrogen. So that's the other colors that you see, the blue, the green, and the purple. The blue is what we call steam methane reforming, the same as the gray. But we had carbon capture and sequestration, meaning that out of a process, you capture that carbon and you will borrow it, so to speak, or you will find a way to store it so it doesn't go to the atmosphere. What you see in green is the green hydrogen. That's not very inventive, right? It means that it's produced from electrolysis using green electricity, like renewable windmills, solar, nuclear. Some people consider it as renewable. I'm not sure we can, but that's the next category anyway, the purple one, in which we have two different processes. Either we can use the excess heat from a nuclear power plant and use that with a solid oxide electrolyzer and get very good efficiency in converting and making hydrogen. Or there are other processes like splitting water with combination of copper and chlorine. Long story short, we have many alternatives. The bad news is that everything is expensive. So in order to implement that, DOE had a target to set up 7 clean hydrogen hubs in the US, subsidizing with $7 billion out of the $40 or $50 billion that we needed to invest. So all right now is a little bit challenged, but long story, I wanted to make that introduction so we understand what's going on with hydrogen. The use of hydrogen right now, the one that you see, is mostly on the top side, meaning we use hydrogen to make fertilizer. I think 55% of the production of hydrogen in the world is directed to ammonia and fertilizer. Some of that, about 25 or 30%, is in the petrochemical industry, and there is very little, as you see at the bottom, for mobility. It's not even 5%. I think it's not even 1% that we have there. So right now, moving to hydrogen engines, you see in the middle, the green pump is supposed to show the greenness of the hydrogen engine.
when you use clean hydrogen. If we try to compete right now between traditional vehicle on the left, conventional vehicle, electric vehicle on the right, which is the next one in terms of cost of a vehicle and cost of ownership at this point. We are still penalized by the cost of a vehicle in commercial vehicle, which means that a truck of class 8 would be about 2 times as expensive as a conventional. Then we have in the middle right the fuel cell, which would be fed with hydrogen and has a fairly decent efficiency, in terms of fuel efficiency. That would be at present the worst solution in terms of cost because fuel cells are very expensive. So we look at an alternative. What if we would use that diesel engine, convert it in a way that it can burn hydrogen, and therefore we have benefit close to what we have with fuel cell? That's not completely true because we have some emissions that do not happen in a fuel cell. Fuel cell, the process is at a low temperature, something like maybe 200 Fahrenheit, and you don't create by association of nitrogen in the air and oxygen, the nitrogen oxide that we get in an engine. So the fuel cell is cleaner, but we have ways to clean, so to speak, the exhaust of these hydrogen engines. So right now, hydrogen engine on a truck would be the third best solution in terms of cost of ownership, so to speak. It depends very much also of the cost of hydrogen right now. Hydrogen might not be very expensive to produce, maybe something like $2 per kilograms if we do gray hydrogen. If we do green hydrogen, it's maybe 4 or 6. But the less visible part is the transportation. If you make your hydrogen 1,000 miles from where you use it, if you don't have a pipeline, it's very small molecule, so you cannot really put much on a tanker, so to speak. If it just compressed, you put 500 kilograms, half a ton, it's nothing. If you liquefy it by temperature, you can put 3 tons, but it's still very expensive to move. So what are the applications that we see? The darker blue is the application that we see for hydrogen engines. It means that it goes from construction truck up to long-haul trucks. Characteristic of long-haul trucks is that we want to have a long range, something like 400 miles, 500 miles. So you need to have that energy on board, which is challenging for a battery EV at this point. If we look at 400 miles, you might know that we need about 2 kilowatt hour per mile for class 8 trucks. So it means that you have a 800 kilowatt hour battery, something like 10 times what you have on a Tesla car. And that will weigh something like 3 and 4 tons. It's not that much space. Maybe it's 1 cubic meter if you relate to cubic meters, but it's heavy. Hydrogen, on the other side, is very light, but the drawback also is that it takes a lot of space. Even if you compress hydrogen at 700 bars, you have something like 42 kilograms per cubic meter, and then with the packaging, it dilutes further to 20 kilograms per cubic meter. And if you want to have 400 miles of range, you need about 80 kilograms of hydrogen, and therefore you need something like 3 cubic meters. That's really a huge place. So when you see, for example, in Europe, they are pushing a little bit more than we do here in the US, hydrogen trucks. It's presented as being a solution for long haul, but if you see the application, usually that's more a demo truck, and because of a regulation in Europe in which you are limited by the total length of a truck, it's very challenging to make it fit. So and that's the reason why companies like Daimler are now trying to push the liquid hydrogen, the cryogenic hydrogen, because it reduces your space needed by a factor 2. It looks like we are not very optimistic on hydrogen. What we see at this point, because of a cost that we have on these solutions, is that we might have maybe 2% of the market that might adopt hydrogen solutions. So that might be also some on the construction side. We have application on the train, but on the vehicle, road vehicle, in many cases, it will be competed by a battery electric vehicle. So it's really very specific solution. And it could be either a transition solution, as you saw. You see, it could be decreasing and go away by 2050. Alternatively, if hydrogen becomes really as inexpensive as we hope it will, and if a fuel cell do not develop as well as we think, there might be some space for these engines. Talking about hydrogen engines, I'm working on trucks, so obviously I like the little colory engines that we have. There are 12, 13 liters, either by, we have Volvo, we have Cummins, we have also DAF and Packard that have been working on that. I think even at the Southwest Research, I think they have been working on these engines. There are other applications also on cars. At the top, you see that Honda and Toyota are big in terms of hydrogen. And we have also on construction, you see JLG, for example, and Liebherr in Germany are working on that. So it's not the only, the main application at this point is the commercial vehicle, but it can expand to others. So what does it mean? That's nice to try to push hydrogen, but is there a good reason for that? So what we have done is that we have made a life cycle assessment of what is the result when you use hydrogen on a truck. So that's just showing that we take into account everything from the source to the processing, to the transportation, to the utilization. And we have been projecting for different states in the US what will be the mix of hydrogen that will be made available. So right now, everything is light blue. Light blue is steam methane reforming without carbon capture. So that's what you see on the left side. And you see that progressively, if you could read that, I cannot read it, but the darker shades are lighter in terms of carbon. So it shows the transition that from a very heavy mix in terms of carbon to something lighter. Actually, I have a better chart to show that. It shows you for the three states that we have considered, California, Texas, and I'm not sure that Southwest is a state, so we might have aggregated New Mexico and different places. But you see that we have an improvement, but it takes time, obviously, to develop that. Hydrogen, as defined by the Department of Energy, is clean when it produces less than 4 kilograms of CO2 per kilogram. So I don't know if you see that little dotted line, but it means that it will take a long time to be there on average. Every addition, yes, can be clean, but obviously it's diluted by not so clean hydrogen. So now I will not make I should have prepared that and have a kind of poll. Is it clean in the end? So what we have done is that here we have compared different trucks. So we take a Class 8 trucks and we make it run between Los Angeles and some places in Texas that I've forgotten the name, and it's going back and forth every day. And in 4 years, we do 700,000 miles. And we compare the life cycle assessment, the production of CO2 for these trucks from the production to the utilization. So what you see, the light blue is really the utilization, the darker blue is the production of a truck. The only truck that has significant emissions from the manufacturing side is the battery electric vehicle, because it takes about, you get about 80 kilograms of CO2 for every kilowatt hour of battery that you produce. So that truck would have something like 50 kilograms if it's a Class 8 offset at the beginning. And you catch up fairly quickly with that if you have clean electricity. But some people are concerned, and rightfully so. In the past, it was very intensive. We have worked a lot on the processes now to reduce the CO2 of the production of batteries. So I will just look at one of the charts, and looking at the left side, which is a conventional truck, and any of the trucks on the right side, which are the hydrogen engines. We have two kinds of hydrogen engines. We'll come to that in a little while. But what you see is that actually, if you just use straight hydrogen mixed right now, your truck is emitting more CO2 than a conventional truck. So that really says that it's no use to do that unless you introduce new production of clean hydrogen. Now, fast forward 7 years from now, in 2030, that mix of hydrogen has already hopefully been improving. And you see that now these hydrogen trucks are slightly better than the conventional trucks. The unit that you see is in kilograms of CO2 per miles traveled for this truck. In all cases, since the electricity is relatively clean these days, I think on average in the US it's 368 grams of CO2 per kilowatt hour. And it comes from a mix because we have a few coal power plants. These are terrible. It's like 1 kilograms of CO2 per kilowatt hour. But we have hydraulic, we have wind, we have some solar. So the mix dilutes down to 368 or something like that. So it's already competitive, even if not perfect. And it's improving also at the same pace, I would say, because we have a lot of production. So it's always difficult to, it might not be easy actually to implement new clean resources, but that's always, there is a drag in that. So long story short, here also the conclusion is that hydrogen truck, there is no hurry, so to speak, unless we implement more clean hydrogen. And finally, we come to a part which is the lubricant requirement. I see a big smile on everybody's face. I think that's a kind of relief, right? All right. So before going into that, it's heavily the requirements are heavily influenced by the characteristic of a fuel, the fuel being in that case hydrogen. And there are 3 or 4 characteristics that I think are important. First one is that hydrogen, when it burns, it's hot. It's hotter than gasoline and diesel, so it's what you might see in the second row there. The temperature when you burn it openly in the air, it's a little bit different when you burn it in the engine because you have compression and things like that, but that gives you an idea that it's very hot. Second thing is that it ignites very easily. That's something that is called something like the ignition requirement. That's a unit that it tells you how big your spark need to be, so to speak, to turn on that combustion. And one thing also is that hydrogen, people love it because when you burn, all you get is water. But the problem is that when you burn it, you get a lot of water. So compared to a normal engine in which you have something like 14% water, here you have 35% in the case of an hydrogen engine, and that might be challenging. And there are some other properties here. It's a little bit wordy, but it tells you that what are the challenges in terms of flammability. One good thing is that the laminar flame, it's much faster than other fuels, and therefore, when you burn, if you look at the efficiency of the engine, if you burn like very quickly, you get a good efficiency of the engine. If it takes a long time, you will start burning also in the exhaust phase, so to speak, so it's not that good. So one property that helps hydrogen engine to be efficient is that high flammability. 3 types of hydrogen engine. I know that I cannot contain the joy here, everybody's. So we have 3 types. On this left, you have the spark ignited, which is port injected. What it means is that you just have an injector at the inlet of an engine and to just blow hydrogen in there. That's the least expensive way to do it, but it literally backfires from time to time because you have a flow that goes back and forth. Also, the engine is very prone to detonation, so we have to control a little bit the ignition. A way to improve that is in the middle with a direct injection. That would be a Cummins engine that is doing that right now, so that controls much better the combustions. And the third way is what we have with what we call HPDI, high pressure direct injection. You actually inject at pretty much at the same time the hydrogen and a small drop, so to speak, of diesel, which works like a liquid spark plug, and everything will burn in a much better fashion. So it has a much better efficiency, and that's really the way to go, we believe. I see that I'm running out of time. Is it okay to continue, or should I stop? Okay. Beside the technology that we have seen, it's also the different manner you will burn your hydrogen. You can burn it with a lot of air or with little air, and for that, hydrogen is very accommodating. It gives you the opportunity to burn with dilute very much a small amount of hydrogen in a lot of air. What is the benefit of that is that during the combustion process, there is interaction between the molecule of nitrogen and oxygen, and they combine what we call nitrogen oxide, obviously. And this is bad for your health. It affects the lungs and things like that. So that's a regulated pollutant. And in order to avoid the creation of this nitrogen oxide, we want to have what we call lean burn or low temperature burn. So that hydrogen accommodates that. The drawback of that is that compared to another engine, you might need maybe 2 or 3 times more air, and therefore it means that in terms of design of the engine, the restriction of the valves, the turbo compressors, and all that needs to be oversized. So that's a little bit of a constraint. Finally, the recommendation. So what does it mean? First, we saw that that hydrogen has a tendency to burn even when we don't want it to burn. So we have to make sure that we don't favor that spontaneous combustion, and therefore that we avoid anything in the oil that would create a kind of little particle that would start burning and therefore ignite the whole load of hydrogen that we have in our engine. So the first element that we want is really the control and avoiding what we call the pre-ignition. The second element is about water management. If you have made mayonnaise at home, you know what I mean. You take oil, you take vinegar, here it's water or nitric acid. That doesn't really work well. So we want really to keep this droplet and to disperse them as good as possible. First, so you keep the lubricating qualities, but also if you have oil, water in your oil, when it's freezing, the water will freeze and you will not be able to pump your oil, and then the engine will not work. First thing that we have, and I think it looks very much like Troy. I was looking at Troy's conclusion. I say, did we mix up or exchange the slides? Because I was seeing oxidation and all these things as stress. Yes, that's the same. Here, actually, we have a lot of stress also because we have high pressure of combustion of this engine. And therefore it puts a lot of stress on the parts. Also, the fact that we have excess of oxygen in that means that compared to another engine in which you turn everything in CO2, so to speak, if it's a diesel engine, here you still have oxygen which will react with your oil, and it will make, I'm not saying margarine, but kind of sludge or something that we don't really want. The fourth element that we have is the oil volatility. We were talking about the flammability of hydrogen. What happens is that there is some blow-by. Blow-by is a term that we use when you go from the combustion chamber along the piston, so to speak, to the crankcase, and then you end up with some hydrogen in the crankshaft. And that hydrogen, again, wants to explode. So what we need is to ventilate to make sure that we have a flow of air that is cleaning up the crankcase, so we don't have explosion inside the crankcase. And since we have a lot of air going on top of the surface of the oil, and the oil is not like like Michigan on a clean day, right? It's a little bit too heavy, right? So you have a lot of things, and we want to keep that evaporation and taking the droplet out. The fifth element is that we need to have a good anti-acid resistance. If you look at gasoline, when it burns, it doesn't, you have some soot and things like that, but when we burn hydrogen, and we might end up with nitric hydrogen, which will combine with oil, so we want to some capacity to neutralize that nitric hydrogen. I would make the parallel in the diesel engine. Diesel, in the content of the diesel, there is some sulfur, even if you have gone with low sulfur diesel in the last 15 years, maybe now, but you create some sulfuric acid with hydrogen with a diesel engine, and in the same way, we need to neutralize that. So I would put the hydrogen engine in the middle between the gasoline engine and the diesel engine. And last but not least, some people, I'm sure we have specialists here, people from Afton or Infineon and things like that, will ask me, what about the low-speed pre-ignition, the LSPI that you see? That's something, that's a phenomenon that started to be seen, better said, maybe 20 years ago with downside engine that were affected by heavier load because it's better in terms of efficiency. They were starting to knock, and we didn't know what it was, so we put a big name on that. We said it's stochastic pre-ignition instead of normal ignition. It's supposed to make you scared, right? Stochastic pre-ignition. It means that it happens somewhere in the cylinder, but not on a deposit or a hotspot. And it has been investigated. And in fact, it was the fact that when you have a direct injection of engine, it hits the wall of your cylinder, which is, you have oil in there. It dilutes the oil. The oil mixed with gasoline was going in the groove between the piston, so to speak, and the cylinder, and at the point of time was ejected. And that was kind of created a liquid that was promoting that pre-ignition. So we have seen that the composition of the oil was very important for that. If you had calcium additive, it would be bad. But conversely, if you use magnesium additive, it would quiet that phenomenon. We have even what we call quenchers of pre-ignition, something that will prevent the pre-ignition. The question was, does it affect hydrogen engine? The answer is we don't think it does, because it's not the same phenomenon. You don't have that liquid jet of gasoline on this prior engine that would dilute the oil. So here it's relatively clean, and we think it will be okay. So finally, I think we can stick to a conclusion. Pretty much the same conclusion as Troy, right? Prevention of oxidation. The pre-ignition is big on the first two types of engine that you have seen, in which we have port injection or injection, but not with HPDI. I see somebody yawning, so that's no good. I should conclude. And basically also the reserve of acidity. The conclusion is that hydrogen engine is certainly something that has a limited place to do in the society. Like everything with hydrogen, it's not just the hydrogen, it's the complete ecosystem. For example, if you have production of electricity that is very intermittent, you might need to have storage alternative for that, and producing hydrogen and putting it in cave and then reusing might mean that we might have hydrogen anyway. So if we have hydrogen, that might be a solution to use it. But it's pretty much depending on the energy strategy of the country also. So I think I have spent way too much time, but thank you for your attention, and we'll move to a panel discussion.
Okay, thank you very much. Can I remind people to use the Slido app to bring questions in? We do also have a microphone for those that are not permitted, do not wish to download the app, etc. So we now move on to the next section. I would like to welcome Rafa Britton to the stage. Pull up the right sheet so I don't make something up. So Raf is a lubricant engineer with 14 years of oil industry experience, split evenly between drilling operations and maintenance and downstream lubricants engineering. During his 12 years at ExxonMobil, Raf worked across some of the largest, most complex CapEx projects in the ExxonMobil portfolio, including the PNG to LNG and Gorgon Jans. He then transitioned into the finished lubricant business, helping industrial customers across the APAC region improve machine reliability. In 2020, Raf started the Lubrication Explained YouTube channel, seeking to help provide freely available, high-quality information about the lubricants technology, create a community of learning for the industry, and connect a wide array of experts. The channel has since expanded into a podcast, Lubrication Experts, an online training business, Lubrication Explained Pro, and led to multiple speaking engagements at industry events. He now works as an independent consultant across all parts of the lubricants value chain. This includes working with base oil and additive suppliers, lubricant blenders, marketeers and distributors, as well as end users. With connections throughout the industry, if Raf doesn't hold the answer to your specific problem, he likely knows someone who does. So with that, I'd like to open the panel session up. We will be, I think, with the questions that I've had come in already, we're going to start on the hydrogen side, and then we'll probably move to the EV side of the discussion. Like I said, microphones there. Please be aware that we will not be getting political today. We may go as far as discussing incentives and that side of things, but not with the moving targets and markets that we have in the US right now. So as the first question, going to come up on the screen at some point, but I shall read it out in the interim. In the green H2 production, what types of demand exist for captured CO2? Are these sufficient magnitude and growing magnitude, or is CO2 storage the primary solution? Anybody have any views or answers on that one? There's a microphone on the table.
Okay, so the question is about capture of carbon. Do we have enough? Here in the US, I am first a disclaimer. I'm not a specialist on carbon capture. I have not seen many projects. I have seen projects, for example, in well, that's not true. There are some projects in the US, but I've seen more projects like in Norway and things like that. But I think in the US right now, it's more in terms of reusing the CO2, for example. The CO2 that is produced might be used for oil exploitation, like a gas to push the oil out of it. So I think at this point, there is not much carbon capture. There is always the question to know also what will be the permanency of carbon capture, how long it will stay in the soil and things like that. But I think from what I've seen, most have been trying to reuse the CO2 at this point, again, in oil exploitation at this point. That's what.
Yeah, I guess maybe I can give an Aussie perspective, slightly different to this part of the world. So in Australia, at least, with one of our major kind of gas trading partners being Japan, and their heavy emphasis on the idea of adopting hydrogen combustion, I think everyone is trying to go down the route of hydrogen production without any kind of CO2 capture, and largely just going the electrolysis route. If you look at Australia as a geography, there's an awful lot of land mass with no people living there. So maybe for an American context, there's one state in Australia called Western Australia. Funnily enough, it's the west of Australia. It's 3 times the size of Texas, but there's only 2.5 million people that live there. There's an awful lot of empty space, and it's real sunny, right? So when I left home, it was 37 degrees, but the Celsius, not the Fahrenheit kind, right? 37 Fahrenheit hits different. So we've got a lot of area, basically, and as the cost of solar starts to decrease pretty precipitously, and that's an area where you're not time constrained, right? So most of the time when we're talking about solar, everyone's worried about the fact that the sun's only shining during the day. Well, you could just have hydrogen production just when the sun's up, right? And that opens up a fair a number of avenues for hydrogen production off the basis of solar. There is no carbon capture or storage requirement in that instance. So it's proving at the moment, the way that the economics stack up, just from my knowledge of the upstream business, that seems to be far and away the cheapest route to hydrogen production. Obviously, with the downside that no one who wants to use the hydrogen lives anywhere close to the areas where you're producing it. So the storage and transportation is kind of the major challenge at the moment.
Thank you. Sorry, it takes a bit to read through the questions and make them make sense. Okay, so the next question that I'm going to pull up is from Ashu Gupta at John Deere. Thank you, Ashu. How do you see commercial engine oils for H2 ICE being formulated? A one solution product, diesel and natural gas and hydrogen, or bespoke H2 engine oils?
I can take a run at it again. So I think there'll probably be a combination, right? It depends on the application. So there are some applications where we're looking at running dual fuel, in which case you don't get an opportunity to switch over the oil system when you switch over the fuel system, right? So there's going to have to be some solutions which are a compromise between both. At the same time, there are going to be very specific applications. So it probably wasn't talked about. Sorry, I came halfway through the talk. But as an example, there's a company called Mayman down in Florida. that's working on a water ethanol combustion fuel, right? So the idea is you use the heat of combustion from the ethanol to vaporize the water, and the expansion of the water as it turns into steam is what gives you the energy for the downstroke on the internal combustion engine. Well, it's not just the lubricant formulation which needs to be tailored for that application, it's all of the coatings on the inside of the engine, because with that amount of water, you're going to run into corrosion issues when the engine's off. So, we can't make up for those deficiencies just with the oil formulation. So there's all sorts of work that's going into, the coatings and the rings and all that sort of stuff there. So I think, it's probably a combination. Maybe in like stationary diesel gensets where you're planning on running it on pure hydrogen, there is certainly a case for running a pure dedicated hydrogen combustion oil. But in instances where it's a dual fuel application, you've got no choice but a single formulation.
Anybody have anything else to add?
No, well, we have seen a dual fuel application also, for example, with in Australia, in which we had a mix of natural gas and diesel engine. These engines, we don't think will have much future in the future, so to speak, due to the difficulty to meet the emissions when we have a mix that is not really easily controllable. So I would foresee more that in that case that we'll go with specialized lubricants like an hydrogen, and even it's interesting, for example, for hydrogen engines, since we have a HPDI, the high pressure direct injection, which are not really exposed to pre-ignition. We might even have different formulation for the different technologies of hydrogen engine that we have.
And just from the standpoint of EVs, I know you're asking a hydrogen question, but I think it's kind of relatable in the sense that the hardware is not going to be standardized. So it's going to be a case-by-case basis. And I would suspect, right, just like EVs today, or at least where they started a few years ago, we're going to take what's on the market available today and try to force it in the application to make it work. And then as things progress, you're going to start getting more and more bespoke fluids based on the hardware. Eventually, as the hardware starts to standardize, then there'll become more standardized fluids. I mean, it's exactly the EV world today.
Right, thank you. Right, so interesting question here. What's the largest H2 production method you've seen in Japan?
I have no idea of the production. In terms of what is the process that would be used, well, if we want to be clean, I think there are not many options. If we want to use a natural source like natural gas, and I don't think Japan has, but we would have a process of pyrolysis in which you would precipitate, so to speak, your carbon in carbon black, and there is not the problem of fugitive or of carbon capture. Still, when you have methane, you have always leak at the well, something like 3 or 4%, and the greenhouse gas potential of methane is very high. It's 20 or 25 at 100-year horizon, but it's something like 80 shorter terms at 20. So I don't think we want to go with any route long term which would be best in methane. It has to be electrolysis. Seeing that Japan is not big in terms of nuclear, I would think that they will have in that case to go with renewable wind and solar and electrolysis. I think that would be the route for them to go.
So kind of transitioning slightly as we move towards the EV questions, I have a question here, which is, what does the future of lubricant recycling and reuse look like? How do we reduce the need for more drilling? So lubricant recycling.
Yeah, so maybe I can address that from an upstream perspective, because I used to be a drilling engineer. So I think that the challenge that we have in the lubricants industry, so first of all, let's say some level of re-refining, recycling, that's a problem that's being worked on, plenty of solutions there. On the other hand, what we do here is not making a massively material change to hydrocarbon demand, right? So it's what every barrel of oil that comes out of the ground, less than 1% of that is getting converted into lubricants. The vast majority of it goes into fuels, plastics, petrochemicals industry, all that sort of stuff. So even if we are able to develop a complete 100% re-refining, recycling solution we are not putting a significant dent in the requirement for drilling. So let's say that off the bat. However, with the re-refining and sort of recycling, all the technologies are there. I think a lot of it is more an infrastructure issue and maybe also a culture around how do we promote the idea of re-refining. So I think in Europe, it's probably maybe a little more, let's say, not advanced is maybe not the word. It's come a little bit further in terms of maturity, even to the extent of it's much easier to re-refine products when they're segregated, right? So if we have an oil bucket for used engine oils versus an oil bucket for used compressor oils, pulling the AdPack out of compressor oils is a significantly easier challenge than it is for your engine oils, right? So even having that waste segregation set up would be a huge step in making re-refining a ton easier. As it stands, let's say, for example, in my home country, everything goes into the same waste oil bin. It doesn't matter if it's antifreeze, coolants, engine oils, hydraulic oils. And so our re-refining industry has a huge issue trying to clean that up. It's a significantly bigger challenge than if we were able to kind of get that infrastructure sorted.
Thank you. Another transition question here. So, just disappeared. What kind of base oils are adequate for H2, ICE, and EV?
I think the short answer is the one that works, right? Supply chain always comes to mind to me, right? I'm the technical guy, I'm not the commercial guy, but EV side of things, there's already been some newer base stocks, especially on the way of sustainability. And when you have a newer base stock, it's only being made in one place, maybe low volume, right? There's a lot of risks from the OEM side as far as reproducibility. How much is that going to drift over time? God forbid something happens at the plant or a natural disaster that shuts the plant down for some period of time, right? A lot of supply chain risk. So while there's new base stocks coming online, to me, it's just more of a risk and a concern until they become high enough volume. But with that said, until somebody starts using them, you're not going to get volume, right? It's that chicken and egg type situation. So as we start looking at some of the big advantages of some of the newer base stocks that are coming forward in the industry, it is giving us a lot of benefits, especially on the maybe oxidative stability or the heat transfer side of things that will help drive these over time. So I think all in all, right, positive future for them, but some risk involved at the same time.
And then another question on the H2 ICE is, which OEMs are leading the adoption of this technology? What's the main drivers to invest into this transitional platform?
Transition in terms of hydrogen engine?
Yeah, transition into the hydrogen engine.
Yes, well, in the US, it's really one. Cummins has been put together an engine, the X15, which is called fuel agnostic. What it means is that this engine shares a lot of features between different applications. It can be a diesel engine, it can be natural gas engine, and now hydrogen engine. So obviously that's a good idea because it will allow to have economies of scale on these engines. Now it's more on the demand side. That might be a little bit softening now if we don't want to enter into this detail. In Europe, there is much more push or pull, I'm not sure, but it looks like push for hydrogen, and therefore we have, Volvo that is adopting, making an evolution, so to speak, of the natural gas engine that they had, that has already that technology of high pressure direct injection that allows to burn also hydrogen in a nice way, so to speak. And we have Daimler has been experimenting also with hydrogen engine. I think everybody has in mind that it can be a solution even in the construction sector, as we have seen with JLG and Liebherr. So there is some traction on that. On the truck side, it could be also for marine application. Marine application, you don't have too much constraint of space for your tank of hydrogen. It could be on trains also. Marine, we'll see. There is a question whether hydrogen or ammonia would be a better solution. ammonia being easier to transport, and it can be also that ammonia would be produced in one place, transported through boats, through ships, and then converted into hydrogen in other countries. So you would have directly a supply of ammonia on board. But I think definitively Europe is thinking of that, and traditionally the countries that use much more hydrogen than we do are Japan, Korea, and to some extent China also. It's very heavily subsidized in China and in Korea.
Yeah, I think that was a pretty good summary. I mean, I think what's interesting, and maybe a shout out to one of the startups that I work with, this company called Decarice over in Sydney. So they're sorting out a way to basically drill new injection ports into existing diesel engines so that you can run them dual fuel on both hydrogen and diesel. I didn't necessarily think that was possible because the way that Cummins, their X architecture works is you have to replace the entire top end, right? And my assumption was that was, around kind of different valve timing for, the different types of fuels. But for whatever reason, this startup has managed to figure it out without adjusting anything on the cams. So there's a whole startup ecosystem that's kind of working here as well. Then among the OEMs, like you've already mentioned a couple of them, I think it makes sense for a lot of the Japanese OEMs. Yeah, we said we weren't going to get political, but just geopolitically, if you look where Japan is and where they would like to get their fuel from, it's very difficult for them with the population size that they have and the land area that they have to generate enough renewable energy on their own. So, importing hydrogen is kind of a way to import green energy for them. So it makes sense for a lot of the Japanese OEMs to do so. But you've even got, like across, let's say, for example, the generator space, everyone who's in the gas engine world, whether it's I guess it's INEO now, INEO, Jenbacher, your Waukeshas, are all working on sort of gas-powered platforms. And even in the turbine world, right? So we haven't really talked too much about future fuels for gas turbines, but again, all the major gas turbine manufacturers are also trying to make all of their combustors hydrogen ready as well. So I think it's sort of basically everyone's playing in the sandpit.
Anything to add, Troy, before we move on to EVs? Okay, so in the interest of equality, we will move on to some EV questions. And so the first question I have here is, which chemistry do you think will be suitable for EVs? PFPE? What sort of chemistries would be appropriate for EV fluids?
I mean, are we talking additives, base stocks?
I think additives, because we've
additives. I mean, it's going to be system dependent, right? If I'm able to isolate all my copper out of the system, some of the really good sulfur type compounds that we use today as additives are great for gearing durability, as long as they can not break down at some of the higher temperatures that might be exposed to in a wet motor or inverter design. But at the same time, you might be more phosphorus type chemistry, which also has a trade-off too, but trying to deal with exposed copper in the systems. So I truly think the chemistry that it's going to be is not used today. I think we're going to find something new that's going to take the place of sulfur in a gearbox that's really going to shine. What that is, I don't know.
Okay, thank you.
Maybe just like another aside, it feels like the chemistries that we have at the moment are working okay, right? It's not like you see hundreds of thousands of EVs broken down on the side of the road. We make a big deal out of trying to, really finesse the needle or fine tune our formulations to improve reliability, and that's fully understandable. But the stuff that we have now works.
So an interesting question, which you can probably answer quite well, Troy, is EV adoption in consumer markets dependent upon government incentives and regulation, or does government support simply accelerate what consumers will demand? The same question for commercial markets.
So, I mean, most people are kind of resistant to change as it is, right? We've been doing the ICE for 100 plus years now. So to transition to something new, something unfamiliar, it takes a push. I think the government's having to provide incentives, kind of drive legislation is probably the only way a lot of this will drive change, because I don't think it'll just happen on its own by itself. However, it's definitely a tug of war type relationship, right? Because the legislation comes out, the incentives come out, especially when the legislation dictates what the OEMs have to provide. And if at the end of the day the consumers aren't buying it, then the government's pushed the company into maybe a potential bankruptcy situation or a major loss of revenue. So they're not going to be sustainable. So again, this tug of war relationship of kind of providing and developing the hardware to meet what the consumers are asking for, pushing the consumer to be comfortable enough to go buy it, but then, and again, not getting political, right? But inflation continues to drive up, which is also going to hinder this whole situation. So where it goes, I don't know. And as I kind of said in my presentation, I think the internal combustion engine as it is today will probably be around for a long time just because of the state of everything.
When we are talking about incentive, we are talking about money. And in fact, there are different elements that are barriers, so to speak, to adoption for EVs. So it's not only the price, but it's, for example, the convenience of the range, being used to it, the familiarity. If we go back to the question of cost, really the incentives are there to try to bridge a gap that we have in terms of cost of a vehicle. If we look at people like Tesla, we think whatever we want of Tesla, but I think originally they had a very good strategy to try to develop a vehicle at a luxury level, which means that people, the price of a vehicle would not be a problem, and therefore they could develop a technology for that, try to trickle it down, and I think the idea of using the small cells, the 1865 and then the 2170 was really a brilliant idea because it was breaking the fact that if you have very low volume, you're very expensive. So we had all that strategy to try to build the technology and then to gain the volume impact that we would have, and then complement if they were not profitable enough with soft offers like the full service drive, autopilot, things that do not cost too much but that have a value and can be sold, and therefore there's a way to bridge the cost handicap that they had. I think what we are talking when we are talking about government incentive is the same, is to try to get people to buy the cars so we get the volume effect, which will have a virtuous effect on the cost of a vehicle, and then for make it more affordable. At the same time, since you have a volume, you will start to develop the infrastructure in terms of charging. So everything is compounding through volume, so to speak, with the incentive. Up to the point, usually, in which you say, okay, enough money spent, now we will have a regulation and we will have to be 20% EVs or something like that, like what CAFE and greenhouse gas free intending to do. So it's really a transition mechanism to bring the competitiveness that is not there at the beginning with low volume. Now there is a curveball, so to speak, is that the Chinese started that maybe 15 or 20 years ago, and the government was really driving that, and you had a lot of entrepreneurship in China and a lot of competition. So obviously they are much less expensive than we are here in the US. And we see in Europe that it's creates a problem more than here because people start buying cars from China. The problem being that instead of having the production locally in Europe, it's come from another country. So it's all that. But basically, when we cannot count on citizenship of people to buy a product that is more expensive, we need to have a bridging mechanism, and I think incentive is the way to do it.
So, should be a fairly quick answer to this one. What should be the cost target for EV lubricants per gallon? Yeah. I don't know. I mean, I would guess somewhere in line with the equivalent of what it is now for driveline fluid.
Yeah, I would think that would make sense, right? So I think people would see it as being in a very similar category. I would imagine that people are maybe less price sensitive to the cost of what goes into to EVs, because it's not like you see that cost on a regular basis. It's not like I'm going to get a service done and it's a line item, right, on the maintenance sheet. So I think basically the cost is whatever you can get away with, right?
And I'm definitely not the commercial person by any means, but if you look at the formulation today, we're typically using a lot of chemistries that have been around for a long time. So they're not something new, something that should be, elevated in price. And at least for me, looking at gear oils compared to like an EV fluid, a lot less additives in general. The additives are typically the higher priced, to my understanding. So I guess theoretically they should actually be lower than a normal gear oil. How much, I think, depends on what type of formulation you put together. But I think cost sensitivity right now is at an all-time high for the auto industry too, because you see vehicle prices going up because of inflation and all the political stuff going on in the world right now is even probably going to drive them up more. But everywhere we can save a penny, we're trying to save a penny. So I would say current targets probably should be even lower than that today.
So, thank you. We have one further question on EVs, and that's aeration and foaming were brought up as a big concern. What design strategies or preventative measures may be implemented to help reduce this?
So I've seen lots of different small presentations and projects kind of in this area over the last few years. Still a lot to be figured out and kind of understood. But kind of I think from a design standpoint, right, if we take a glass of beer at the bar, right, you have all these bubbles in the bottom. The longer it sits there, the longer they work their way out. If I have this big pool that's flat like a bowl, it's going to be a lot shorter time when I'm trying to pull oil or fluid off the bottom, right, to try to allow that air to release. So from a sump design standpoint, I want to have more of a beer glass than a bowl, so I have time for that air to release. So there are design strategies from a gearbox standpoint to try to, create as much time as possible for air release, the entrained air to come out. Pressure drops through the system as well, right? You have a high pressure pump in most of these systems that might be pushing dissolved air or pushing entrained air to be dissolved air for some period of time under pressure. But then as they come out into an open atmosphere gearbox or motor inverter cavity, again, some of that turnover is going to allow for some air release. But then design strategy is about trying to minimize the creation of it. So turbulent flow is ideal for heat transfer, but obviously not, benefit for aeration level. So trying to find areas where the fluid can sit, not be aerated, maybe not have a high-speed gear sitting in the fluid. Today, like a normal axle, your ring gear is going to be half submerged or somewhere in that area. But we're only talking a few thousand RPM typically at max speed, where you might see 20 or 25,000 RPM out of the high-speed gear on the motor shaft. So if that's sitting in the sump, it's going to be a big issue. There's also a fine balance of trying to minimize the fluids in these systems for weight, for cost. You're turning it over at a high fluid rate. So again, trying to design a system where it's not hitting the gearing, it can settle as much as it can, allow the air to come out, is critical for hardware design. The fluid design, I'm not a formulator, but obviously a lot of surface tension plays a role to try to drive the air out of the system. And then you get different additives, different molecules that will kind of inhibit some of that dissolved air from happening so it can work its way out faster. So there's definitely strategies around what we can do today.
Thank you, Troy. Let's jump back to H2 briefly. So do you see any interaction with the liquefied natural gas international trade trying to grow with the global H2 trade?
I mean, yes, in the sense that they are the obvious players to be doing the transport of hydrogen. So whatever future fuel that it ends up being, whatever future fuel mix that ends up being, whether it's methanol, ammonia, hydrogen, I mean, these are the guys who are sort of well placed because they've got the supply chain set up. They've got most of the equipment set up. Most of the R&D is also being done, with these guys, and it goes all the way through the transmission process, right? So let's say, for example, there's a company called APA which owns about half of all of Australia's gas pipelines. They are looking forward to, okay, well, if there's going to be hydrogen production, how much hydrogen can we put through our existing pipelines with existing infrastructure? is there any retrofitting that we can do to our existing infrastructure to accommodate hydrogen? And what kind of new infrastructure are we going to need to build in order to be able to satisfy that sort of hydrogen, supply chain? So, yeah, I think all the existing players will be carried over into whatever comes next.
So
There might be some complements, so to speak, because some countries, if we look at Chile or Spain or some of the Middle East, they don't want, some of these countries first don't have natural gas, right? So they cannot export it, but they want to export something that might have a higher value or a higher value added, so to speak, than natural gas, and therefore countries, again, like Chile, would like to have production with solar or wind and produce their hydrogen and export it to Europe in the same way as Spain, which is much closer, might have a pipeline for distribution. So I think it will be really a complement, more interest effectively for people who want to have a natural gas and convert it in hydrogen, but also direct production of hydrogen and transport. And transport is really the challenge at this point. We don't have really a good way to transport long distance hydrogen other than pipeline on land, so to speak. But and solution are to either transport it in the way, so to speak, of ammonia and then reconvert. Or I think there is a Japanese process which use toluene or something like that. You associate a molecule, a binder, so to speak, and after that you strip it. That's a Kyoda or something like that. So hopefully we can find better ways to transport hydrogen to make it less expensive.
Okay, thank you. So one alternative fuel we've not discussed this morning is ethanol. Does anybody have an opinion on the lubricant requirements for ethanol engines?
Ethanol engines have been around for a long time. If you look at Brazil, for example, they were big on that. So, and I'm not very knowledgeable. It sounds like since it's coming, well, if it's coming from production like sugar cane and things like that, it would have a good footprint. I think here in the US there are some concern, for example, with ethanol, that is produced from corn, and the fact that we might divert some crops or increase the cost of the crops and make it less affordable for countries that are developing countries in terms of food. So I think it will be really up to some countries to stand by it, like again Brazil. I think we still stand with ethanol. I don't see that we'll see it developing in other countries like in the US unless we switch the production maybe from food-based crops, so to speak, to some other linear or other kind of feedstock, so to speak, in order not to have that problem of competition. And again, when we are with ethanol, we still have the same challenge like with gasoline or diesel, that we need to have after treatments. It's not completely zero emission in terms of pollutant like NOx, particulate, aldehydes, and these things.
Any thoughts on the lubricant requirements for running these engines?
I don't know about that now. So
I mean, from what I've seen, it's not too dissimilar from the other engine oils.
Yeah.
So I don't think it's like a revolution there.
Okay, so we have just over 4 minutes left, and we have 2 questions, which I'd like to get through if possible. 3 actually, but let's take this one. Any chance we can have a lubricant in the future that cleans instead of pollutes for any type of mobility solution? Which one of them would be easier to obtain, this cleaner lubricant? Yeah, which type of technology would be easier to obtain a cleaner lubricant? Would it be hydrogen, EVs?
Not entirely sure what that question's asking, but I'm trying to think of a type of lubricant that cleans instead of pollutes. So, just trying to brainstorm here. So, I think like a potential example could be PAG-based, oils. I mean, that's potential, right? So, and the only reason I'm thinking about that is because number one, the kind of the solubility of PAGs means that they tend to be relatively low in terms of deposit formation. But also the way that they decompose is they kind of like unzip and turn into volatiles and just sort of disappear. So you wouldn't have as much deposit formation. From memory, Chevron used to sell a fuel additive that was PAG based. The idea was that it would volatilize in the combustion chamber and it would just turn into volatiles. So in terms of like the cleanest possible lubricant, I would imagine that could be a direction that you'd head. Yeah.
Okay, thank you. And since we have a few minutes left, it's not specific to this alternative fuels section, but what newer uses do we envisage for fluids in the future outside of automotive? Stick a whole load of automotive people on the stage and you don't get an answer.
Or maybe I should answer this question because I'm industrial. Ultimately, I mean, the way that I think about our industry is just like, if it moves, it needs us, right? So whatever future technology comes out, so long as there's moving components or so long as something needs to be cooled, that's an opportunity for our business. I know everyone's kind of looking at data centers as sort of like being the savior of our industry. Everyone kind of like looks at the volume and lusts over it. I don't know that that's necessarily going to happen, right? So there's plenty of data centers that don't require oil cooling at the moment. And maybe we get to a stage where they want to be super efficient and they need oil immersion cooling. But personally, I wouldn't necessarily bank on that. And beyond that, it's just, if we see, for example, a take-up in manufacturing and a reshoring, then all of those applications are going to need us. Potentially, with more robotics, that maybe skews things more towards the grease side. I think it's interesting there when you look at the robotics manufacturers. If you split them basically between Japan and Europe, all the European manufacturers mainly seem to have gone for oil lubricated, whereas the Japanese manufacturers are mostly going grease lubricated. So maybe there's some sort of differences around there. But yeah, that's the way I think of that. If it moves, it needs lubricant.
Okay. Well, that concludes our session this morning. Thank you very much for attending and thank you very much for your questions. I'd like to thank our 2 speakers and 3 panelists for helping out with this session. Thank you. So just a couple of things. I'd like to remind you that on the Slido app, there is a survey, industry survey. If you'd like to complete that industry survey, if you attend the Thursday morning session, the results from that will be given out on that session. We can now have a short break. We'll be back at 11:30. So track 1 will be optimizing grease performance through additive development and sample analysis. And track 2 will be mechanical engineering challenges and fluid development for hybrid vehicle architectures. Thank you.